Hello dear students. In today's class, we will try to understand what are called as the vacuum drifts. So, in the previous class, we have studied the gradient drift and the curvature drift. So, we also mentioned that the magnetic field imposes a condition that any particle has to always experience both the drifts together. That means the curvature drift and the gradient drift will always be together. So, the magnetic field being non-uniform kind of imposes that the field line should always be curved, and when a charged particle travels across the magnetic field or the magnetic field line, due to its mass being circulated around a radius of curvature, it experiences a centrifugal force away from the center, and this force again was told to give a drift which is called as the curvature drift. So, we have seen all these aspects. So, we have derived expressions for the curvature drift and the gradient drift. So, the curvature drift was denoted with VR and the gradient drift was denoted with V del. So, the field alignment that we have taken was such that the magnetic field, the original magnetic field was perpendicular to the gradient in the magnetic field, and there was a curvature radius of curvature RC, due to which we have calculated the curvature drift, and this particular field alignment, the magnetic field being perpendicular to the gradient of the magnetic field, has given rise to the gradient drift, right. So, we can write the gradient drift and the curvature drift in a more convenient form. So, what we will do in today's class, we will try to see how we can combine these two drifts in a single expression, and we will do this for a situation, let us say, called as vacuum. So, we demand that the magnetic field the region is a source free region, that is, there are no charges which are present, there are no currents which are present, and the magnetic field, the nature of the magnetic field is inherent, let us say. So, we have seen that the V del is equals to plus minus m V perpendicular square divided by 2q Bz dou Bz by dou y across x cap. So, this is the expression that we have derived. We can more conveniently write this as V del is equals to m V perpendicular square divided by 2q times B cross del B divided by BQ. Now, if you substitute your magnetic field to be along Bz and del Bz to be along positive y direction, you will still get the same relation, right. So, or if we say that half m V perpendicular square is the perpendicular kinetic energy, we can write V del as W perpendicular divided by Q times B cross del B by BQ. B cross, this is the magnitude of the magnetic field. Now, similarly, we can also write the curvature. So, if you take the curvature RC, so in order for the curvature effects to be reasonable, or in order to highlight the effects of curvature, because there is one more radius that is involved here, which is the RL. In order to make the effects of gyration or particles movement across the radius of curvature, we say that the radius of curvature is much larger than the radius of gyration. So, in that case, we can say that the curvature drift can probably be written here itself, so that we can understand the full picture. So, the curvature drift VR was derived to be 1 by q m V parallel square divided by RC square times RC cross B divided by B square. So, let us call this equation as equation 1 and let us call this equation as 2, right. Now, so in the last class we have seen that any particle will always experience these two drifts together, that means the total drift. So, V total is written as V due to the gradient and V due to the curvature. So, in this class we will try to understand how we can combine these two drifts. For a special case of magnetic field, we will assume a particular type of magnetic field and its variations along different directions and its components along different directions. Then we will, in that particular case, we will try to combine how we can combine. So, we will try to this class is going to be how do we combine 1 and 2. Okay. So, we will say that. So, for now our objective is V total is equals to 1 by q times m V parallel square divided by RC square times RC cross B by V square plus m V perpendicular square divided by 2q times B cross del B divided by B square, right. So, the idea is if you have a magnetic field, the velocity component that is parallel to the line of force is V parallel and the velocity component perpendicular to it is V perpendicular. So, we have assumed that the gradient was in this direction and the magnetic field was in this direction and the radius of curvature was assumed to be this. So, this is the configuration that we have assumed. So, for now what we will do is we will take this in a so for combining, let us say these two curl terms, these two cross products. So, we will try to get, instead of these two cross products, we will try to get one cross product. So, now one very important inference here is that V total is the total drift velocity is perpendicular to RC, is perpendicular to the magnetic field and is also perpendicular to the gradient of the magnetic field, these three parameters. So, so we have seen what will be the consequence of this particular alignment, in which the total drift velocity that is attributed to a particle will be perpendicular to the radius of curvature, the magnetic field and the gradient of the magnetic field. So, this is why we said that the V total will probably be in x cap direction to facilitate the formation of the planetary ring current, the equatorial or the toroidal ring current that flows around the planet is called as the planetary ring current, right. Now, so let us say we transform this into cylindrical coordinates. So, just to be sure, so I hope all of you have had some introductory class where the different coordinate systems were explained and how these different coordinate systems are different, or how these coordinate systems can be used for different situations. So, the cylindrical coordinate system is very simple. So, if you take this to be if you take any point P which is lying on this, let us say this point, this is the point P. So, now you want to identify the coordinates of this particular point. The cylindrical coordinates come with r, phi and z. So, your coordinates are the Cartesian coordinates are x, y and z. Now, what you do is you draw an imaginary plane, let us say like this, an imaginary plane like this, right. So, the idea is you assume the point that you want to represent with coordinates to be lying on this cylinder, and the angle that it subtends, if you draw a plane like this, the angle it subtends. So, let us say if you want to reach to this point P, in the anti-clockwise direction, the amount of angular rotation that you have to do so as to reach this plane is referred to as phi, and the point P's distance from perpendicular distance from the xy plane is referred to as z, and r is simply the point the points P, the point P's intercept onto the z axis is r, right. So, this is the basic idea of the cylindrical coordinate system, right. So, what we will do for today, we will assume a particular geometry of the coordinates of the magnetic fields such that, let us say, the magnetic field lines are curved like this, right. Now, the radius of curvature is this is r c, right. Now, the coordinate system is assumed to be this. So, this is the phi direction, the phi cap. So, the magnetic field is directed in the phi cap direction, right, and the centrifugal force is going like this, and this direction is the r cap. So, we take the field such that it decreases with r. So, if you go further apart, the magnetic field lines will be placed farther away, right. So, the idea is, now you have a radius of the center of this curvature, and the radius of curvature at this field line is r c, right. Now, the magnetic field line, the original magnetic field line is pointed in the phi cap direction, and the gradient, see the magnet, I am saying that the magnetic field lines are placed farther apart as you go across r. That means, as you move away from the radius, the magnetic field lines are moving further apart. That means, the magnetic field strength is decreasing as you go away. So, the gradient is oppositely directed. So, right. So, the magnetic field can now be written in the cylindrical coordinates, or the components are Br, B phi and Bz. Now, Bz, there is no component of magnetic field across z direction, right. Bz is 0, Br is also 0, but that, what does it mean? Br being 0 means there is no magnetic field in the direction of r, but the magnetic field B phi is not 0. The magnetic field is indeed directed across the phi direction, but this magnetic field B phi will vary as a function of r. So, magnetic field which is directed in the phi direction will have different values at different values of r, but the magnetic field is always directed across the phi direction, right. So, that is the basic idea. So, the magnetic field can now be written as B is B phi as a function of r, and which is directed in the phi cap direction, right. Now, so now we know we will, with this type of magnetic field, now let us say this is the type of magnetic field that we have taken. Now, is there a gradient? Of course, there is a gradient across the r direction. Is there a magnetic field? There is a magnetic field along the phi direction, right. Now, with this type of magnetic field, we will try to assume, we will try to combine these two cross products. Now, where is the z component missing? I mean, so the z component is out of this page, right. So, z component is this out of the page, which is the z component. So, again the phi component, magnetic field is directed in this direction along phi cap. The strength of the magnetic field is decreasing as you increase the value of r, and there is no magnetic field component across the z direction. So, simply we have transformed this into the cylindrical coordinates, right. So, let us say, let us call, we will try to see how we can combine both the types of magnetic fields, right. Now, let us say we know from the Maxwell equations that del cross B, the curl of the magnetic field in cylindrical coordinates can be written as 1 by r dou Bz by dou phi minus dou B phi divided by dou z along r cap plus dou Br by dou z minus dou Bz by dou r across phi cap plus 1 by r dou by dou r of r B phi minus dou by dou phi of BR across z cap, right. Now, if you substitute B, the magnetic field's components, we can write the curl of the magnetic field as del cross B. Why is the curl important here? The curl is important here to find out the gradient and the curvature drifts as 1 by r times 0 minus 0 along r cap plus 0 minus 0 plus 1 by r dou by dou r of r b r minus 0 across the z cap. Right. So, we just have substituted all the different components of B. So, from the Maxwell equations, we know that del cross B is equals to mu naught times J plus dou E by dou T, J plus dou D by dou T, right. So, in vacuum, we say that del cross B is equals to 0. That means the products that we have calculated del cross B. So, that means that, see, from here what we say is that the del cross B, since this is 0, has only z component, right. So, del cross B has only the z component. So, del cross B, the z component of del cross B was calculated to be 1 by r dou by dou r of r b phi, which is actually equal to 0. That means r b phi is just a constant. So, let us say with this constant we call it as capital A. So, the magnetic field B phi is A by R. What does it mean? It means that the magnetic field is changing with respect to the distance as 1 by R. But does it also mean that the magnetic field has a component across the R direction? No, it does not mean that. It simply means the magnetic field is directed in the phi direction, but it varies as a function of R. This is the basic difference. So, now let us say we say that dou B phi by dou R now simply becomes minus A by R square, which is also equal to minus B phi by R. Now, B phi is A by R in phi direction. So, if we use R is equivalent to RC, we say B phi is equals to A by RC across phi direction, right. So, this is the magnetic field. You call it as B phi or B. We simply call it as B, which is equals to A by RC in the phi direction. Now, we will take a ratio, let us say the ratio of the gradient of magnetic field's magnitude divided by the magnitude of the magnetic field is equals to minus A by RC square directed along RC divided by A by RC, which is equals to minus RC cap divided by RC, which is equals to minus RC over RC square, right. Now, coming back to the gradient drift velocity term, which is equals to minus plus half V perpendicular RL divided by B square times B cross del B. Now, what have we done so far? Let's look back before we continue. So, what we have done is we have taken a certain type of geometry for the magnetic field and its gradient. So, if this magnetic field is true, the curl of the magnetic field should look like this, let us say, and having substituted the magnetic field's components, which are, let us say, for example, along the z direction it is 0 and along the r direction is also 0. It has only one component, which is the phi component, which is varying as the distance varies. So, we have done that. We realize that the del cross B will only have a non-zero z component. Now, for the vacuum, let us say in the absence of any source, any charges or any currents, we say that the del cross B will be 0. That means the z component of the curl that we have derived should also be 0. So, in that case, the magnetic field B phi, or you call it as the B itself, because B does not have any other components, B phi should simply be A by R. So, if B phi is A by R, dou B phi by dou R simply becomes minus A by R square. We are calculating, or we are evaluating at a distance of R is equals to RC. So, we have substituted R is equals to RC in this, right. So, then we have calculated the ratio of the gradient of the magnetic field, only the magnitude, divided by the magnitude of the magnetic field turns out to be this, right. Since this is a gradient, it is a vector, right. Now we are getting back to the gradient drift velocity formula that we earlier had. Now, let us say this, I will simply rearrange this equation for convenience. Let us say V perpendicular RL by B square times B cross using del B from equation number 1, let us say, as B times RC divided by RC square, right. So, which is equals to plus minus, there is a minus and the cross product can be rewritten V perpendicular RL divided by B square RC square times RC cross B into B. So, we cancel this B. Now, we will get plus minus half V perpendicular MV perpendicular by QB times 1 by B RC square times RC cross B, which is equals to plus minus half V perpendicular square divided by omega C times 1 by RC square B times RC curl B. So, we will write it as V del B is equals to plus minus half M by Q V perpendicular square RC cross B divided by RC square B square, right. So, we know that this is the gradient term, the curvature term is already written as a curl of RC and B, MV per V parallel square by QB square into RC, again curl of RC times B RC square B square. No. Right. So, what have we done? We have done that B cross del B term is transformed into RC cross B term. So, this is for the del part, and for the curvature part we already had the curl in terms of RC cross B. So, we can be able to combine, let us say, these two together. So, V total is now V del B plus VR, which can be written as m by q times V parallel square divided plus V perpendicular square divided by 2, the factor 2 coming here, into RC cross B divided by B square RC square. So, this is the V total. So, this is the total drift velocity that the particle experiences when it encounters a inhomogeneous magnetic field whose magnetic field lines are curved, right. So, like I said in the last class, this drift velocity is perpendicular to RC and B, and this also seems to be dependent on the charge. So, V is proportional to 1 by q. That means the direction of V will be in the positive x cap for electrons and in the negative x cap for the ions. So, then we have seen that for a geometry like this, the field, the particles will move to the either sides of the earth, constituting a current which is called as the ring current. Now, we very well know with any drift velocity V d, the current density J can be written as N Q V d, right. Now, the current density due to the gradient drift velocity can be written as J del is equals to, let us say, N Q V del. Let us say N I, the number of ions per unit volume, is equals to the number of electrons per unit volume, which is equals to capital N, let us say. We write J del is equals to N Q E into V del I minus V del E, right. And similarly, we can simplify it even further by substituting the expressions for the gradient drift velocity. We will write N by B cube, W perpendicular for ions plus W perpendicular for electrons times B cross del B. So, similarly, we can also write the velocity, the current density due to the curvature term as N Q V R I minus V R E, which is equals to 2 N by R C square B square W parallel ion plus W parallel electron times R C cross B. What is this? This is J R. This is the current density due to the curvature drift, and this is the current density due to the gradient drift. So, these two are responsible for what is called as the planetary ring. The planetary ring current becomes a very important phenomena when you want to study the geomagnetic storms or space weather fluctuations in the Earth's atmosphere, right. The planetary ring current is typically of the order of several million amperes and whose strength keeps changing with the amount of plasma that sun throws at the earth, right. So, we will have more detailed discussion about the planetary ring current when we discuss topics about geomagnetic storms or things like that. Okay. In this class, we have been able to combine the drift velocity due to gradient of the magnetic field and the curvature of the magnetic field. We have got rid of, instead of having two curl terms, we have one curl term and both the velocity components, parallel and perpendicular component coming into the picture. So, this drift velocity is mainly responsible for the creation of what is called as the planetary ring current. So, in the next class we will discuss something called as the magnetic mirroring and how it enables particles to be trapped within the magnetic field. Okay.